It's a great honor and pleasure to welcome you here in the audience. And we also have an audience out there in the real world and also in the second world. You know, you have probably heard about Second Life. We are broadcasting these talks into the Second Life, which is a virtual reality world which can actually do almost as good as the real world. We also have a group of people. Where are they, JD? In Oregon, yes, we have a group of people in Oregon watching as a group, and I would like to thank Sifan, who has put up all the Second Life and the broadcast here together with JD, who is our local hero. And before we go into the very exciting topic of the evening, it's really the discoveries are raining down on us, and it's really amazing, even for us as professionals, how quickly our knowledge is improving and increasing. But I always say, while our knowledge is increasing exponentially, our ignorance is increasing even more, because with every answer, we are seeing 10 closed doors that still need to be answered. So this is really very exciting times. I would like to thank in particular the friends of Institute for Astronomy. They are huge support. They have supported all these outreach events, and today in particular. And so please, if you want to help and join the friends, sign up out there. There is, when you're on your way out, there's a sign-up sheet, and then you will be informed about events, and you will become part of our Ohana. And then we can move on to the next slide. This is where you can see our social media presence. We have Facebook, we are on Twitter, we are on YouTube. Roy Gall, who is our outreach coordinator, is doing most of that work. He has baby duty today, so he was in here in the beginning, but unfortunately cannot be with us. But he's probably with us in Second Life. And sorry. If you are interested yourself, or you know somebody who is interested in pursuing a career in astronomy, we have something. Can we turn the lights down a little bit? We have something very exciting. Since about 2 years, we have started an undergraduate program, actually 2 undergraduate programs in astrophysics and in astronomy. And actually we have the first people graduating in that program, and we are hoping that this program will become one of the largest in the country. And this is basically only appropriate because we have also the best observing sites in the world to also make these observing sites available to our young kids. And in addition to the undergraduate program, we also have started an outreach program with the high school and middle school kids. We are the only place in the world where a high school student can actually write a proposal and apply for observing time. And then when the whole class is writing a proposal and they are competing with each other, only a few students are getting the observing time, but the whole class is going to observe. So we bring high school students over to the telescopes, and that is also a very important element. But now let's come to the real topic of tonight, KILONOVA, and it's a great honor and pleasure to introduce to you Ken Chambers. Ken Chambers is the director of the Pan-STARRS Observatory, and he is really tireless since many, many years to keep that observatory working, and to also in parallel build a second telescope which will see first light very soon. So very soon you will see twice as many discoveries from Pan-STARRS than today. Maybe different because the Pan-STARRS 2 can provide different qualities and can follow up on our own discoveries. So it is really very exciting times. Ken has started his career over on the East Coast in Baltimore. He has worked at the Space Telescope Science Institute and has graduated from the neighboring Johns Hopkins University. And then he has done something that is rarely done. He went to Europe. I come from Europe and I'm working here in the US. He went to Europe for a postdoc to the very famous European University Leiden, where he was working with George Miley on radio galaxies, quasars, and that is still his pet project. But he has, in the meantime, opened a much more dynamic chest of astrophysics, and we will hear today about the exciting discoveries of the kilonova. So please give a hand to Ken Chambers.
So this is an artist's representation of two neutron stars as they spiral in. And you see this, I will try. I'm as close to the mic as I can get. Is that better? And so these two neutron stars are spiraling into each other, and they will finally crash together. These are the hardest things in the world, in the universe. And you see the supernova, I'm sorry, the kilonova, being powered by the radioactive decay of the heavy elements that are being formed. And the glow here is powered by radioactive decay. So, my name is Ken Chambers. Good evening. Aloha. I want to tell you tonight about an extraordinary campaign in astronomy, the first of its kind, I think, really, in the history of astronomy, and it's an extraordinary story. It's also a complicated story. I'll do my best to try to pull all the pieces of the puzzle together and make sense out of it. But it has shed new light on all the matter that we are familiar with, even some of the atoms that are in your body, even some of those atoms that make you feel the way you feel. So that first part, I apologize for the cheesy Star Wars intro. That's actually a tribute to my father, who's 96 years old. And he actually worked on that Vela. This is a true story. He actually worked on the Vela instrument package. And the Vela packages were put up there to look for violations of the Test Ban Treaty back in the 60s. And they were looking for the Soviets testing thermonuclear warheads in space. Turns out they never did any testing in space. But Vela did find this strange gamma ray bursts coming from the universe. And at the time, it was all top secret, but it was recorded. It was reported later in the literature. But it took a very long time to follow up. We think now of NASA of doing it's always doing scientific exploration. Back in those days, it wasn't. It was to put men on the moon, and that was its mission. So it took almost more than 20 years before NASA went back and put the Compton Gamma Ray Observatory in space, and it found that these gamma rays, strange, mysterious bursts of gamma rays coming from the cosmos, were actually quite common. But there was no way to get a good location and identify where they were coming from. So another NASA satellite called the SWIFT satellite was able to pivot. And so it would detect gamma rays, and then it had an X-ray detector, and it would pivot, and it would look, and it would identify a region in space, and then the ground-based telescopes could go after it and look at them. And what they found was they could deduce by the fact that these things were spread uniformly in space, and they were so bright, and they were identified as being so far away, that they had to be like a lighthouse with a beam pointing right at you. You only saw them if they were pointing right at you. And if they were pointing away from you, you wouldn't see anything. So we never had a chance to see what was the underlying object. We only saw it when we were looking right down the throat of this incredible beam of radiation that was relativistically boosted. But people had ideas about it, And so for a while, there was this idea that two neutron stars would merge together, and when they crash together, and again, you think of two pool balls crashing together, they're very hard. Oh, neutron stars are really, really, really hard. They're the hardest things there are. And it would put out a jet, and out that jet would be the gamma ray burst that would go out along the axis of the merger. But what would it look like from the side? Well, that was termed a kilonova. Well, why kilonova? So this is a joke over here where the two astronomers are talking and saying, yeah, somewhere between a nova and a supernova, probably a pretty good nova. That's what a kilonova is. So a nova, that's short for new star, nova stella. And novas are stars that get new fuel from a companion and they burst and they're quite bright. But supernova, that happens at the end of the life of a massive star. And they're very bright. They can outshine an entire galaxy with hundreds of billions of stars for a few weeks. So a kilonova is somewhere in between. So it's much fainter than a supernova, it's brighter than a nova, but it's actually produced by only a few percent of the neutron stars that come out of the collision. And so we'll talk about that. And then this happened. So what you're hearing there, that little ding, that chirp, it's called a chirp, that rise in frequency is if we take the gravity wave detected, and this is actually a compression and an expansion of actual space that's doing that chirp, and then about a second later, we saw the gamma rays. But this time it wasn't pointed right at us, so the gamma rays were very, very, very faint compared to normal. So this happened this year, August 17th, at 12:41:04 UT was when those two neutron stars merged according to the LIGO, Laser Interferometric Gravity Wave Observatory, and it was detected by Fermi. And actually, Fermi reported it first because Fermi's reports are all automated, and LIGO had just added a new antenna to the field, and it took them a while to get everything working. And that delay meant it was a little bit of time before the astronomy world learned of it. But when it did, the astronomical community went nuts. And there's nothing crazier than a bunch of astronomers who are really excited. And it launched this armada of telescopes of all kinds, of all sorts. Almost every telescope on the planet, whether it was in orbit around the Earth, whether it was out in space, whether it's on the Earth, stopped what it was doing and started to look at this thing. More or less in a pretty unorganized fashion, but that's the way it happened, and it's quite a story, and that's part of the story I want to tell you tonight, but also so that you try to explain what's really going on in the underlying physics of why this is so exciting to the astronomers and why everyone dropped what they were doing and went off to look at this. So, sadly, we need to talk about a whole lot of things because this really is a big, big, big story. And I got to try and pull all the pieces together so that you can appreciate it. And I want you to try to walk away with some understanding of why this is so interesting and how we know. How do we know the things that we know? When we say that we know that a certain star has magnesium, how in the world do we know all that? So we got to talk a little bit about chemistry. We've got to talk a little bit about light and spectra. Got to do some nuclear physics here. The life cycle of stars, we got to talk about the curvature of space, detection of gravity waves, the kilonova explosion, this origin of the elements, and what all this means for you. So that's a lot. That's a lot on the plate, and I will do my best to try to pull that all together. So please bear with me and hang on, because it really, really is an incredible story. But to get all of that, we got to go through all of these different things. So all matter, everything, people, animals, ocean, all material stuff is made out of elements. These 92 elements, hydrogen up to uranium. There's a bunch of ones that are heavier than that are radioactive. They're not stable. We won't worry about those right now. So 92 stable elements, and everything is made out of those 92 elements. Everything that you can touch, feel, smell, sense in any way, shape, or form. And these are all atoms, and the atoms, you all know this, are made up of the nucleus down in the middle, which is made up of protons and neutrons, and electrons whirling around the outside. Okay, this picture is pretty common. Of course, it's very inaccurate because the nucleus is actually 1,000,000 times smaller than the size of the atom. It's very, 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 very small, down deep inside. Okay, and the protons are positively charged, and the electrons are negatively charged, so they're attracted to each other. And the protons, because they're positively charged, they want to get out of that nucleus. They're repulsive to each other, and the nucleus wants to come apart. But the neutrons are there to hold it together. So if you got enough neutrons in there, you can hold that nucleus together, and you have the positively charged center, and you've got the electrons whirling around the outside. Now, you all recognize the periodic table. It's been hanging in your classroom since you were a youngster, and you may not have looked at it recently, but there's these 92 kinds of stable elements. You might not have counted up the rows recently, but there's 2 in the top row, then there's 8 in the next 2 rows, then there's 18, then there's 32. And that comes because these 2 actually fit in here, and that turns these rows into 32. And those numbers come from the filled electron shells. And so when the electron shells are filled, you get these ones on the far side. These are the noble gases, and they don't like to react with anything because they have filled electron shells. It turns out the structure of the nucleus has a similar property. We'll get to that. But we're astronomers. We can't put a star in the laboratory. We'd like to, but we can't. And we can't analyze what it's made out of in the laboratory with laboratory equipment. We need a different tool in the toolkit. And that, we have to rely on the properties of light. So when astronomers say light, what we're really talking about is the electromagnetic spectrum. It's called the electromagnetic spectrum because light is actually waves of electromagnetism. And what we see with our eyes, the visible spectrum here, is just a tiny fraction of the entire electromagnetic spectrum. You've got gamma rays, which are these very high energy rays, very short wavelength. The wavelength is getting longer and longer here. X-rays, ultraviolet light, the visible light that you can see with your eye. Then redder than red is the infrared, the microwaves, just like what you cook your food with, and the radio. So all of that is the same stuff. It's just electromagnetic waves at a different frequency. And almost all of astronomy until now has been based on some region of this electromagnetic spectrum. We now have a new spectrum. We now have gravity waves, completely different, nothing to do with these. But the light can contain a huge amount of information, and a simple example of light is something you're very familiar with, is light from something that emits light just because it's hot, like the element on your stove. It glows red simply because it's hot. The light is coming from it because it's warm, because the atoms inside are moving back and forth quickly at their temperature, and they emit a very specific spectrum. So this is the spectrum of something that's at 7,000 degrees. This characteristic shape is the spectrum that you get from anything that's hot. And this is the intensity of how bright it is here. This is the wavelength from going from blue to red. This is the part within the visible range that you see with your eye. So the sun's about 5,000 degrees in the outer parts, in the photosphere, and it looks yellow. And your stove element is about 4,000 degrees, and it looks red when it's hot. You don't want to touch it. And something that's really, really hot actually looks white to our eyes because you see all of these colors together. But that tells you can derive from this spectra, you can tell how hot something is. So if you have a thermal source like this, the way you find out what it is you put an instrument on your telescope, and there's lots of different ways to do this, but the simplest way to think about it is a prism, and it breaks it up into the colors of the rainbow. So this is wavelength in this direction, and how bright it is this direction. And if it's just something that's hot, it has this characteristic shape. Now, if you put a gas cloud in front of it, what happens is some of the atoms in that gas cloud get excited, and they jump up to a higher electron shell. And when they do that, the energy that it takes to do that is removed from the spectrum. And so you end up with this thing where you're missing bits of light. And these dark lines are a fingerprint or a barcode of what the element is that's in that cloud. So that's how we can figure out what kind of atoms are in this cloud. Now actually, the atom after a while gets tired of being in that excited state, and it drops down and it emits. And you'll see an emission line spectrum, which is just the opposite of this. And so you can look at it either it may be along your line of sight, or you may just be looking at the gas cloud, and you'll see these two different ways of looking at it. You'll see an absorption spectrum where you're missing some light, or you'll see this very specific lines at very specific colors. And each one of those is a fingerprint. So here's the periodic table again, and all of the elements, you recognize the shape as the periodic table, and in each one is the spectrum of each one of those elements. So here's how you can tell what things are made of. You can look at it and you say, here's iron. That must be iron. Or here's hydrogen, here's helium. You can work your way through. So you can compare what you see at the telescope with what we know from the laboratory of what these different elements are. Now in reality, that's a little bit too simple a statement, because it actually depends on how hot they are, what the pressure is, what the density is, what their ionization state is. So this actually gets pretty complicated to try to do it, but you get the idea. Each atom has its own fingerprint, and so you can work backwards to find out what atoms there are. Now here's something that's equivalent to the periodic table. It's very important to this discussion, so let me take a moment to go through it. You may have seen it before, or you may never have seen it. This is the chart of the nuclides. It's the periodic table of the nucleus. So on the left here, we've got the number of protons going up. So each line across here, as you step up here, going up higher and higher and higher, is more and more protons. You're working your way further and further and further up the periodic table. And this direction is the number of neutrons. And you see you need more and more and more neutrons as you go up to higher, to the heavier elements. Well, you need those more and more neutrons to hold it together, because all those protons are trying to rip the nucleus apart. And you need more and more neutrons as time goes on, as you build up more and more heavier elements. So you get this funny structure that comes from these lines. These are nuclear magic numbers. That comes from the solution of the quantum mechanics for the nucleus. And they're different from the ones in the periodic table. So the nucleus has different periodic structure than the electron structure that determines the chemistry. So the nuclear physics is different from the chemical physics, and the elements fall into different kinds of categories than they do in the chemical periodic table. Now, at any given element, like iron, you may have several different isotopes. So everything here has the same number of protons, but you've got different number of neutrons that are still stable. So you have the same element, but different number of neutrons. That's called an isotope. And so that's key to this whole game, because we can get these isotopes by two different processes. So it's important to understand that for each element, typically you don't have just one kind of nucleus. You have a family of nucleus, all with the same number of protons, but you can have multiple numbers of neutrons, and these are all stable. Once you get away from these black ones, you can still have these nuclei, but they're not stable. They don't last for very long. They're radioactive decay. In fact, inside this whole region, these things will last for some short period of time, and then they'll decay. But they can, and sometimes the lifetime here could be milliseconds, very, very, very short. But you can create all of these nuclei for a short period of time, and then they'll decay. This gray part is the part that we've measured in the laboratory. This blue part is what we think is theoretically possible. So as you're marching up and down this thing, you're going up in atomic mass, you're going up the periodic table through all the elements, and you have these different bands. You've got these ones down below iron. You've got this range in here, this range in here, this range in here. Those are all different structure of nuclei, and they have different nuclear properties. So the key question for tonight, what do we want to try to get to tonight? We want to understand what's the history of every atom on Earth, because the nuclei haven't changed. A few do. They're radioactive. They come and go. They might get changed a little bit. But most of the nuclei in every piece of material, in your body, in the chair that you're sitting on, in every hard thing you talk about, that nucleus has been there since the formation of the solar system, and even earlier. And so the question is, where did that come from? They've been recycled countless times, right? Your mother ate her dinner, some of that food ended up in you, became your cells, et cetera, et cetera. You grow up, you live, you die, you go back into the ground, your atoms get recycled again in this circle of life. But the nuclei haven't changed. So the question is, where did our nuclei come from? What's our cosmic DNA? Where did the nuclei of everything that's on Earth and in the cosmos, where did it come the first time? Where did it form for the first time? And how did it end up in Earth and in our bodies? Well, to build up the elements in the periodic table, you got to start from the most fundamental element you can. The first one is just a single proton. Again, protons are positively charged. If you smash two of them together, you can get one of them to turn into a neutron and emit an electron or a neutrino, and get deuterium. And you can go through this process starting off with 4 protons and ending up with 2 of those having turned into 2 neutrons, and you end up with a helium atom. That's called the proton-proton chain. That's what's going on right now in the center of the sun. That's what the sun runs on. It burns hydrogen, which is 1 proton, into helium, and the warmth from the sun that you feel comes from this. It's producing this gamma ray radiation, which is very high energy, but it's producing it down in the middle of the sun, and that poor little photon of gamma rays has to work its way all the way out from the center of the sun. It actually takes about 1 million years for a photon to work from the center of the sun out to the outer parts of the sun, because it collides so many times. It takes this incredible random walk on its way out through the sun. And then finally, when it leaves the surface of the sun, it's lost all of the energy from all those collisions, and it's coming out, and the surface of the sun only looks like about 5,000 degrees. So it's lost a huge amount of energy along the way. So this is what's going on in the center of our sun. There was a time in the Big Bang, in fact, it was about 3 minutes after the Big Bang, when the entire universe was as hot and as dense as the center of the sun. That's why we call it a hot Big Bang. It was much hotter and much denser earlier than the 3 minutes, but at about 3 minutes after the Big Bang, 3 minutes after creation, the universe had cooled to about the same temperature and the same density as the center of our sun right now. And the same reaction went on in the universe, and it produced helium. So when you go to the grocery store and you buy a helium balloon to take home to your friend or your child or whatever, that helium was produced in that first 3 minutes. But then the universe kept expanding and cooling down, and it couldn't build up any more nuclei. If the Big Bang had been a little bit slower, and the universe hadn't expanded quite so quickly, it could have burned further. And the universe could have burned all the way to iron. And then we would have a very, very dull universe. We would have a universe that was nothing but iron. Well, that wouldn't be very exciting. Fortunately, the universe expanded quite rapidly and left all this free energy in the hydrogen and the helium that could be then burned today in stars. By the way, these gamma rays that come out here, that's what that Vela satellite was looking for in the hydrogen bomb. And hydrogen bomb does the same thing. It fuses hydrogen, that's why it's called a hydrogen bomb, puts out gamma rays. That's what Vela was designed to look for. Okay, well, you get the idea. You can build up bigger and bigger nuclei from the smaller ones. You can take 2 heliums and you get beryllium. You take beryllium and a helium, you can get carbon. You can keep going. You can take carbon and helium and make oxygen, take helium and oxygen and make neon, take helium and neon and make magnesium, and you work your way up carbon and oxygen together, get silicon, and you work your way all the way up to iron. So you can produce everything in that periodic table in these nuclear reactions, and all you need is a really hot, dense place, right? The center of stars. It has to be hot because the particles have to be moving really, really quickly to overcome their repulsion. These nuclei are all positively charged. They don't want to, like pushing 2 magnet poles together, right? They want to go away from each other. They're positively charged. They want to repel each other. The only way you overcome them and get them to get together to the point where they will fuse is by having them move very, very quickly. And you do that by having them very, very hot. And the way you get this thing very, very hot in a star is the gravitational attraction of the gas in the star is pushing down. That's heating it up, and then the fusion is the energy coming from the fusion heats it up, makes the gas hot, tries to push out, and you have this balance between gravity coming down and energy coming out of the fusion, and that supports a stable star for a while. But ultimately, you run out of fuel. So a massive star, in the last day before it explodes in a supernova, has this sort of onion ring structure. It's got a little bit of hydrogen going on the outside, then helium, oxygen, carbon, neon, magnesium, silicon. Down in the middle, you've got this iron ash. And the iron is literally ash. It is the most tightly bound nucleus, and it won't burn any further. Just as you have a campfire and you've got the ash left over, you can't set the ash on fire. It's already burnt as far as it's going to burn. But once you get to the center and you've got nothing but iron ash in the middle, the fire in the star goes out. There's nothing producing energy anymore. The star collapses, bounces, explodes back out, and you've got a supernova. And now you've got all this wonderfully enriched material that started out as hydrogen but built all the way up to iron, blown out into space. And that can now go into the formation of new solar systems with all this enriched material. And so you have this life cycle of building up all the heavy elements through the life cycle of stars and blowing them out into space for the next generation of stars. So we started out in a universe that was completely, had only hydrogen and helium at some point. And today it's full of all these 92 elements that are stable. Where did the ones greater than iron come from? So this just shows that the iron is just the nucleon, the binding energy, and iron is the most tightly bound nucleus. So you can get energy all the way up to iron, but after here, it takes energy to put nuclei together. Okay, where are you going to get the energy to put something together like that? So you can't burn iron anymore. It's the ultimate ash. So we need another way. If we're going to get the rest of the elements in the periodic table, we need another way to add material to the nucleus to build up the heavier elements, okay? But to explain that other way, I got to talk for a little bit about something called beta decay. And that's something funny about the neutron. The neutron by itself isn't actually stable. As far as we know, a proton will last forever. But a neutron will last for about 11 minutes, 11 and a half minutes. And then it decays into a proton and an electron. So this has no electric charge. Proton has a positive charge, an electron has a negative charge, so you still have no charge. You haven't violated conservation of charge. It kicks out an antineutrino. We won't worry about that. Okay? But the only reason a neutron is stable, the only time a neutron is stable is when it's inside a nucleus. Then it's calmed down a little bit, and it won't go through this. On the other hand, if you can get it to do this in a nucleus, you get a neutron to turn into a proton, well, inside a nucleus, if you've now gone up to one more proton, you've jumped up to the next element in the periodic table. So the whole trick is to get a bunch of neutrons to get tickled into going into protons and building your way up and up and up and up and up the periodic table. That's how we get the things heavier than iron. Okay, so how do we build things heavier than iron? We use neutron capture. You need neutrons, okay? Now there's two ways to do this. There's two possible things, and there's actually two different kinds of isotopes. If you go into the periodic table, you can divide them into these two kinds of isotopes, the S-process isotopes and the R-process, and that's just the physicist's way of saying slow and rapid. So the slow process isotopes, they can only be formed in a very slow fashion. The R-process one's very rapid. And this can go on in stars. You can get these S-process isotopes. You get a neutron every 1,000 years or so or something like that. And then it'll decay and it's created a proton and it's stepped up one in the periodic table. That's great for filling in the cracks in the periodic table, but it isn't going to get you there in the first place. To get you there in the first place, you need to flood a nucleus with neutrons. You need a tremendous amount of neutrons all at once. Get one of them to turn into a proton and step your way up the periodic table that way. So we've known this from laboratory work for a long time. The question is, what kind of astronomical environment could you have that would give you this kind of incredible neutron flux to build your way up? And what I learned when I was a student, and what I think is still in the Astro 110 textbook, if you go to the bookstore today and buy it, and what's being taught in the Astro 110 class, is that happens in supernova when they explode. There's lots of neutrons. Those neutrons go through this R process and step the way up. I'll show you tonight that's not right. Or I'll try to convince you. Okay, by adding lots of neutrons to a nucleus very, very quickly. You've got to do it before this thing decays. So you've got to do it really, really quickly. You can get one of them to turn into a proton and step up the periodic table one step at a time, building up the higher elements. So if we go back to this chart of the nuclei, up to iron, we build these up through this fusion process going on in stars, but we've got to get all these other ones. So what do? You add neutrons, and then you get beta decay. Add a neutron, beta decay. Add a neutron, beta decay. Each beta decay turns a neutron into a proton. So if you keep flooding this thing with neutrons, you can work your way up from the bottom here to get up to this valley of stability of all the stable elements that we have in the world today. Okay, well, there's actually a couple of different steps in here, and I've purposely tried to color code them. Between a neutron number of 50 and 82, these are these magic numbers. It's analogous to the noble gases and the electron shells in the periodic table. These are places that are especially stable nuclei. So you have especially stable nuclei at 8, 20, 28, 50, 82, or 126 neutrons. And those are sort of bottlenecks in this process. So if you flood it with a lot of neutrons, if you flood it with a lot of neutrons, you can get these light R-pros elements. If you flood it with an awful lot of neutrons, you can get the R-process lanthides. So these aren't, lanthide is a term in the periodic table it's a chemical description, so it's a bad name. Astronomers are great for putting bad names on things. So only some of these are lanthides, but some of them are. And then there's the actinides, which includes things like uranium up here. And then you need a really lot of, a real truckload of neutrons to try to produce these. And you're fighting, in uranium, you get up to ones that can start to do alpha decay, which is a different kind of radioactive process. And so they're kind of leaking out as you try to build them up. So it's tough. So we divide this chart of the nuclides into these three different ones. The light R process, which I'll illustrate in blue, the R process lanthanides, and the R process actinides, the very heavy ones. All right, so what do we need? All we need is an awful lot of neutrons. And the whole thing has to happen in minutes. Because remember, that neutron's going to decay in about 11 minutes. If you don't get it sunk up in a nucleus in that 11 minutes, or half an hour, because that's the half-life, right? Some of them will last a little bit longer, but not much longer. So you don't have much time. So you need an awful lot of neutrons in a very short period of time to build up all those heavy elements. Well, where in the world are you going to be able to do that? Well, let's go back to this story of the life cycle of stars. First of all, stars form out of some gas cloud. The gas and the dust that are there condense into a pre-stellar nebula, and eventually it gets dense enough and cold enough that it can collapse, and then eventually it forms a star. And if it's a small star like ours, like the sun, it'll last for a very long time burning helium. That's what our star is doing right now. But someday it's going to turn into a red giant. Okay, when it's used up all its hydrogen, then it starts to burn helium, and then it expands in this red giant. And when it does that, when our sun does that, it'll engulf the Earth. The sun will become as big as the Earth's orbit in our solar system. And we're toast at that point if we haven't figured out another place to go to. And then eventually it turns into a white dwarf in the center, and it sheds off all this material. And you see beautiful pictures of these planetary nebula, and it's put that enriched material back out into the interstellar medium, where it can go and form a new star, and you get this cycle of material getting ever more enriched by these stellar processes. And you're left behind with a white dwarf. Those are cool and interesting, but we're not going to talk about them tonight. Or you get a large star, and that eventually blows up into or expands into a red supergiant. And these are ones that burn all the way down, their centers all the way down to iron, and collapse in a supernova and throw all that material again, out again, which can go back to form new stars. So it's another means of enrichment. And what's left behind, there's two possibilities. Either a neutron star or a black hole. If the initial star was very heavy, maybe 100 solar masses, it's going to produce a black hole. Maybe 30 solar masses, produce a neutron star. And these three things, the white dwarf, the neutron star, the black holes, these are the ultimate ash of the nuclear burning in stars. Okay, these are the dead end. This is as dead end as you get. You get a white dwarf, you can't do anything more. It's just going to get cold and cool over time, and there's no new energy to be extracted from it. You've squeezed every possible bit of energy out of it. Same with the neutron star, even more compact, very dead end state. And of course, the ultimate end state, the black hole, you've gone down the black hole, there's no coming back. That's what a black hole is. So these are the end states of stars, and once you've gotten to them, that's it. There's no way to extract any further energy out of it. Just for illustration, here's the size of a neutron star, so something like 1.5 or 2 solar masses, like the mass of the sun. But the sun is enormous, of course. Compressing it down into something that's only about 12 miles in diameter, it's very, very dense. And it's very, very dense because it's essentially one giant atomic nucleus. Okay, all that matter that was in the star that went in to produce this, everything, all the electrons have been pushed together with the protons to make a neutron, so that you've got nothing but neutrons left. And then all the neutrons are all packed in very closely together, and you've got this incredibly dense object. So if we were really in this situation, it wouldn't look like this, because the Earth would go and end up a thin film, one nuclei thick, on the surface of this neutron star, just by the gravitational attraction. So it's a very unreal picture, because it's just going to and be a thin film of nuclei on the surface of the star. But that shows you the size of it. So incredibly massive, incredibly hard, much harder than diamond, hardest thing in the universe. So here's a neutron star, something like 1.5 times the mass of the mass of the sun, but only about 12 miles in diameter, and it's got some solid crust of nuclei, maybe about 1 mile thick, with lots of different ions in there. And then inside, you've got this liquid bath of neutrons. It's actually a Fermi bath, and you can't compress them anymore because they have spin, and you can't put 2 spin things, more than 2 in the same space. That's the Pauli principle, but don't worry about that. You get just pack them in really, really, really tightly. Maybe in the center they even come apart into their quarks. Each neutron's made up of 3 quarks. And so maybe in the very center, you've got a warm core of free quarks, but this thing's not going to go anywhere, and it's not going to do anything. Okay, so no neutron stars, these are cool, but they're also as dead as can be. So there's no energy left to do anything else, right? Well, maybe you remember this scene. Here's Luke looking out at the sunset, thinking about how he wants to get off Tatooine or wherever he is. And he sees this, and he sees 2 stars setting, because his planet is in a system with 2 stars. And when I was a kid and I saw this, I thought, oh, wow, that's totally cool. How unusual. No. Most stars are in binary systems. This is more common than not. Our system is the weird one with only 1 sun. Stars like to come in pairs. They like to have a sibling. We almost had a sibling in Jupiter, right? If Jupiter had been 10 or 20 times bigger, we might have had a little brown dwarf in our neighborhood, or if it had been much bigger, we would have had our own binary system. But Jupiter was a little bit too small. But stars like to come in pairs. And some stars are going to form neutron stars and black holes. So sometimes you're going to get a pair of neutron stars and a pair of black holes. It has to happen sometime. Okay. So before we go any further on down that path, we're going to go pick up another piece of the puzzle. And so we're going to talk a little bit about curved space. So imagine, if you will, a situation where we have 4 bowling balls above the Earth. Here's the Earth down here. You can see the curvature of the Earth. And you've got 4 bowling balls, and I've tried to put them in a perfect square. Okay, and you know, according to Newton, there's a gravitational force from the center of the Earth pulling on each one of these bowling balls. And the one that's closer feels a stronger force, because the gravitational force falls off as 1 over r squared. And the one that's furthest away feels a slightly less powerful force. And these two feel something intermediate. So this is going to accelerate the most and this the least. But Newton's law is kind of weird. It says you have a force between two objects, right? If I have an object over here and an object over here, I got to keep the mic near my face, so I got to use the end of my elbow. Okay? If you move this one over here, Newton says this one over here feels that gravitational force immediately. There's no way for there not to be instantaneous. And Newton himself didn't like that. Action at a distance. He didn't like that, but he didn't, you know, his real genius was to keep going even though he ran into something that bothered him. He kept going, and we had Newtonian physics for a long time. But what Einstein did was, well, let's go back to the Newtonian picture. What happens after they're falling for a bit? After they're falling for a bit, they separate because this one's accelerating faster, this one's slower, these two are intermediate. And that square that we had to begin with has now stretched out, not into a regular shape, but into a kite. These two are closer than these two, okay? So in the Newtonian picture, they're falling because of their gravitational force, their attraction to the Earth. But in Einstein's picture, they've just moved through curved space. And because they moved through curved space, their relative positions have changed. And space is curved, and you can detect it by these things falling. Well, sometimes we use to describe this three-dimensional curvature of space that Einstein said gravity is due to this curvature of space and space-time as 4 dimensions. Well, it's kind of hard to draw the curvature of 3 dimensions. It's very hard. Nobody knows how to do it. So what we do is we draw it as 2 dimensions. And so we say, well, okay, in Einstein's theory, gravity, in his theory of gravity, mass is characterized. If you have mass, it's going to curve the space around it. And so you can think of it as a rubber sheet, and you put a ball in it, and it pushes it down. And space is curved, and it's curved because of the existence of mass. And people have even argued that mass is that curvature of space, that they're one and the same. But look what happens. You've got this grid. Out here you have squares. As you get close to this mass, what happens? Same thing. The squares turn into diamonds. Okay? So this does represent the way things fall in Newton's theory to a first approximation. Okay? So this stretching of material, that really does work like gravity. And you've heard of these other things that have curved space. So here's the sun that curves space a little bit. Here's a white dwarf, which is very, very dense, and it curves space a lot. Well, a neutron star really curves space because it's as dense as you can get. It's the closest thing you can get to a black hole without being a black hole. Well, a black hole, the curvature goes to infinity, all the way down to infinity. That's what we call the singularity of a black hole. And so the curvature there, the curvature of space gets incredibly curved. Okay, well now let's go back to our binary star. Suppose you've got 2 binary black holes or 2 binary neutrons, and they're going around to each other, and each one of them curves space in the same fashion because they're massive and they're dense. And when they're orbiting each other like this, they distort space, and these ripples in space-time propagate outwards. Okay, so as they orbit around, these ripples go outwards, and it takes a lot of energy to ripple space. Space is unbelievably stiff. It's even stiffer than a neutron star. Space is the stiffest stuff. And so as these things put this ripple into space, what happens? That takes energy. The 2 of them lose energy. And they lose energy as they're orbiting each other, so they start to spiral in. So you might think it takes forever for these things to spiral in, but no, as they're radiating this gravitational radiation, as they're losing energy by curving space and orbiting each other, that curved space, they've got to use all their orbital energy to curve space and send this ripple out. They get closer and closer and closer together. Well, that's a one-way trip, right? There's no way to stop that process. Okay, so how do we detect that? Suppose that's happened out there in the universe. Well, that's what it looks like up close, is that ripple. But nearby, what you get as a gravity wave passes through us, because we're a long ways from the source, is that stretching and compressing of space. It stretches out, and compresses in and stretches this way. So it says the squeegee. So space actually does this. So on August 17th, when that wave passed through the Earth, you went, okay? You really did. And the space in each one of your atoms went, okay? You didn't feel it because it's very, very small, but that's what the entire Earth went, because space itself went, okay? Space itself expanded and contracted as that wave went through. Now, how do you tell that? I'm saying that, but why should anybody believe it? Well, let's measure, so you got to measure the distance. If space really expanded and contracted, if you measure the distance between two different points, you'll see that happen. Okay, and you can measure distances very accurately with a laser. Okay, you have it, you can set it up, you bounce the light off a mirror, so here's a mirror, bounce it back, you can combine it, you can measure the distance incredibly accurately. It turns out to be the most precise measurement we can make, and it's unbelievable, and I'll show you that in a few moments. But here's how you do it. This wave goes through. I don't know if I can get this to... Can't get it to run again, but it does this squeegee back and forth. That changes the distance between the mirrors. You can detect it. So that's how we can measure that this wave went right through us, every one of us. Okay, so here's the way it works. Here's a schematic of the LIGO interferometric gravity wave. You have a laser, you send it out, you bounce it off the mirrors. This is a half mirror, so some of the light bounces off and some of the light goes through. It's half silvered. It goes down to a mirror at the end, bounces off, comes back. It's going at the speed of light, of course, so this happens very, very quickly. The other one's doing the same thing. And then they come in, and they can either be combined destructively, like these are. They're going to cancel each other out because they're going in a different direction. Or if you change the distance back and forth of these two mirrors, you can make them constructively add together or destructively go away. So this thing either gets bright or faint, if the mirrors move. So when a gravity wave goes through, the mirrors get stretched, and you're sitting here with a detector, and you're measuring that those mirrors are moving. And that's how this system works. But boy, do you need a lot of hard work to do that. So here's the LIGO observatory, 2 laser interferometers. Each one of the arms, this is one in Hanford, Washington. Here's the United States down here. There's one over here in Hanford, Washington, and another one in Livingston, Louisiana. And they're about 3,000 kilometers apart. And each one of these has 2 arms, the same thing we just saw in the schematic. So you send a laser down off a mirror and come back. But these arms are about 4 kilometers long. And you do that experiment, and then you compare the two. And if you see something in this one and you see something in this one, then you can at least triangulate it back to a circle in the sky and see where that source came from. So LIGO's arms, they're so long that they got to take the curvature of the Earth into account. Okay, at the ends, they got to prop them up by about 1 meter so that they're actually straight because the Earth is curving away underneath them. That's how big this thing is. And inside you've got the tunnel. You can tell from the trucks how big this is. You know, a little door here. Okay. Inside the vacuum tube, you're at ultra high temperature. You can't have anything getting in the way of that laser beam. It's got to be really, really, really empty. So a very, very high vacuum, and you've got to maintain that over this 4 kilometer vacuum tube. That's pretty tough. And then here's that schematic. So you've got a squeegee wave coming in, and it moves the arm back and forth and the arm back and forth. It can measure a change in the length of a 4 kilometer arm to 1 part in 10 to the 23 zeros. 1 part in 10 to the 23 zeros. That's a distance of 1/10,000th of an atomic nucleus. The technology to do this is amazing. The fact that we can measure 1 part in 10 with 23 zeros after it, this is the most precise measurement science has ever made. And the technology is phenomenal. And this is an absolutely beautiful experiment. So the physicists built this to test, built the LIGO interferometry to test Einstein's theory. Now, they did that. They got the Nobel Prize. That's great. They got the Nobel Prize in October. We were all very happy for them. Beautiful, beautiful experiment. Now let's do astronomy with this thing. Okay? Because now you can start looking for stuff and use this physics experiment for doing real astronomy. Well, inside you've got these, so the guys are in the bunny suits to keep this thing super clean, and you've got these mirrors, and they're supported by these are quartz fibers that they're hanging from a very sophisticated suspension system. And here's another picture inside. They've got these various alignment and test mirrors and everything. This whole thing has to be aligned and set up just perfectly. And it's got to be isolated because any vibration will start those mirrors swinging. So you can't have that. So this very, very fancy vibration isolation system up on top. So they have all these detectors to detect everything. They can, the Washington one sees the waves pounding on the beach on the west coast. You can see a truck going by. You can see, of course, earthquakes are a big issue. All this sort of stuff. Even the molecular vibrations inside the mirrors, because the mirrors aren't perfectly cold, throw this thing off. So they have all kinds of instrumentation all over the place to measure that stuff, and then they try to counteract it actively. So this stuff manipulates the wires holding those mirrors, moving them in just the opposite way to try to keep that mirror absolutely stable. It's an incredible experiment. It's phenomenal. And it works. So here's a nice video of this curvature of space. Again, you're looking at the two-dimensional curvature of space. Here's two black holes. As they rotate together, here's the clock ticking down at above. So at the end, this goes very, very quickly. So that's in seconds, okay? And you can see the curvature of space. They're black holes, so the curvature goes to infinity down at the bottom of that hole. And as they spiral in, they're putting out these gravity waves. These gravity waves are going out into the universe, and they're losing energy, and they get closer and closer and closer. And the end result, there's no going back. You're going to end up with another black hole that's actually not as big as the two together because you have lost a lot of energy going out in the gravitational radiation. That's an interesting aspect of this. So you end up with another black hole that's a little bit less than the sum of the two you started with. Well, okay, LIGO's cool, and it can detect a merger of binary neutron stars, but it doesn't give you, all you've got is this triangulation from these two antennas, one in Washington and one in Louisiana. There was a third one brought on board in August, which was really important because in Italy, called Virgo, and the combination of Virgo and LIGO together enabled us, the physicists that are running the LIGO Observatory and the Virgo Observatory, to pinpoint it reasonably well, but reasonably well is hundreds of square degrees. That's not very precise when you're looking for a single point of light. So, how can we search? So it gives you a very large region. We call it an error bar region. How big, what's the probability in contours that the source might lie inside it? How do you search that large region of the sky quickly enough to find the right object? Because remember, there's other things happening in the universe. There's supernova going off all over the place. Well, that brings us to the University of Hawaii Pan-STARRS system. This is our baby. It's up at the top of the summit of Haleakala. Here's Mauna Kea in the background. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. It's a funny name, not my idea, but we've come to like it. So this is the Pan-STARRS telescope. This is the Pan-STARRS 1. Pan-STARRS 2 is just a little bit to the left. And we've been using this telescope to survey the sky over and over and over again in different filters to build up this color image. So this is the entire sky. This is the Milky Way. This is what you can see from Hawaii. And the Milky Way goes around us, but when you lay it out, it looks like this. We can't see down here. You'd like to have the entire sky. Down here's the South Pole. Can't see the South Pole from Hawaii. Get pretty close, but you can't see all of it. If you printed this image, so this was our final image. We call it the 3 pi steradian survey. That means 3/4. That's a mathematician's way of saying 3/4 of a sphere. So we've got 3/4 of the sky. If you printed out this image at full resolution, it'd be 1 kilometer by 2 kilometers. And you'd get down on your hands and knees and look at each little tiny star and galaxy that would be just barely visible on the piece of paper. This is an unbelievable image. This thing has been compressed incredibly. These images are now available, by the way. You can go to the panstars.stsci.edu and download any part of the sky and have a look. So we've gotten all of this data out there, and the catalogs have all crawled over these images, analyzed all the objects, characterized them, put them in a giant database. In fact, our database is, I think, the largest astronomical database in the world right now. And this image catalog, the set of images, is the largest set of astronomical images available. All right. Well, we've got this map of the sky. Oops. Let me go back. The best part about having this map of the sky is here's the state of the sky at some point in time. If something changes, you go and you look for a change. And things are changing all the time. Okay, so the way Pan-STARRS finds asteroids or near-Earth objects or interstellar objects or supernova or kilonova is to go and take another image of the sky, because we keep doing this. We keep surveying the sky over and over and over again. And then you subtract it off and you see what the difference is. And if there's something new there, you're going to see it. And we see new stuff all the time. We find about 2 near-Earth objects every night. We find about 12 new supernova every night. There's supernova all over the place. There's not enough telescopes in the world to go follow them up. Most of them, we find them, and that's that. Maybe they get picked up by somebody else, maybe not. Hopefully, the interesting near-Earth objects get picked up, and the interesting supernova somebody goes after. So we're putting all this stuff up, and we rely on the rest of the world to go after them with their telescopes. Okay. Well, now we have everything in place to be ready for August 17th of this year, when, I remind you, this is what happened. So that chirp are those mirrors in LIGO going back and forth faster and faster and faster as the black hole or the neutron stars spiral in and spiral in and spiral in. And as they spiral in, the frequency goes up, 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 all the way up. And then the gamma rays come out. That's a little ding. So this launched this armada of telescopes to find this thing. Here's what LIGO did. Fermi, which is the spacecraft that did the gamma ray stuff, didn't localize it very well, just this big giant patch. There was another gamma ray experiment that gave this stuff. That's not very helpful. LIGO by itself gave these 2 green bananas. This other gravitational wave observatory, Virgo, in Italy, that had just come on board and only been on board for a few weeks, narrowed the region down to this. And this event was unusual. We were very, very, very lucky because it was quite nearby. And by being nearby, there weren't, it's strange but true, but from the gravitational wave information, you actually get the distance. So you start to know there's a shell of galaxies to look for. And because it was nearby, there weren't that many galaxies at that distance in this error bar. If it had been further away, this would have been very hard. It would have been perfect for Pan-STARRS because Pan-STARRS would survey the whole area and we could do it. But this one, the astronomical community was very lucky because it was nearby. We were a little unlucky because it was in the southern hemisphere and harder for us to get at. Everyone was a little bit unlucky because its angular separation from the sun wasn't very much. So the sun went down, and then this thing went down only about an hour and a half later. So we only had a very short period of time to study it before it set for the night. So what happened was the folks on the SWOPE telescope, and one of the members of that team, Benjamin Shapi, we had just hired here at the Institute for Astronomy, brilliant, bright young guy on the discovery team that found this thing. So obviously we made a very good decision in hiring him. And they found that compared to in this galaxy, which is NGC 4993, And they did this by eye. They did not do this by computer. They did this by eye. I had a graduate student blinking these things. And they saw this thing here. And they put out this message that said, okay, we found something that's somewhere near this error region. But was it associated with the gravity wave? Like I say, there's supernova going off all the time. All you've got is one observation that says, bing, something new here. It could have been a supernova, was most likely to be a supernova. Well, it was still daytime in Hawaii. So we jumped up and got ready with pan-stars, and we went after it, and we already had, because we had mapped the whole sky, we had this nice little galaxy, NGC 4993, and here it is before the gravity wave hit. This comes out of our survey picture. And then by the time the sun went down and we could get after it with pan-stars, in Hawaii it was 16 hours and 55 minutes after that ding had happened, and pan-stars went after it, and yep, sure enough, this thing was here. If you subtract this image from this image in the computer, you got the difference. There's the difference. It's a blue KILONOVA. And we were able to say, yeah, in the short period of time since they saw it in Chile at the Swope telescope, and by the time it turned to night in Hawaii, about 6 hours later, this thing had faded dramatically. And so we were able to say, wow, that thing faded faster than any supernova. That's no supernova. And that helped the rest of the world decide, oh yeah, okay, this is not some false signal, this is not some random supernova. This particular object is the one. And the Armada was launched. And everyone went after it with all of these telescopes trying to measure stuff in space, gamma rays, X-rays, all the telescopes trying to get photometry, spectroscopy, everything we could of it. And this really was an extraordinary thing. Now, one of the things that people have questioned about this effort, so the way this worked was all of these facilities signed an agreement with the LIGO folks, a memorandum of agreement that they wouldn't put their information out early. So it was sort of like there was a closed club. But it wasn't really a very close club because virtually every observatory in the world made this agreement with them, so it was a little silly. But they did that originally because the physicists that built LIGO were worried that their first signal would be so weak. Okay, we now know that the first couple of signals they saw, which were black hole mergers, the signal was so strong and so clean, nobody questioned it, and they got the Nobel Prize in October, right? But before that happened, they thought, well, maybe it won't be clear. Maybe we'll just have sort of a marginal result. But the astronomers will go and find something, and they'll be able to prove it, and then they'll get the big cheese, right? So they made this whole series of agreements to set up to protect the physicists from the astronomers beating them to the punch, which was reasonable, so everybody signed it. But it kept the information inside this sort of closed circle, and people have been critical about that. That won't happen in the future. Now that we're past this first one, it's all opened up. Anybody can go after everything. But it did lead to some interesting interactions because astronomers are rather individualistic, and trying to get them to work in a big group like this is like the herding cats routine. It's not easy. So there was lots of personality in this effort. But here's what's going on. Here's the Milky Way. Here's zooming in. These are the LIGO probability contours. So the most likely place is here, but of course it's not in the most likely place. It's off somewhere else. And we're going to zoom into this thing. And this is how hard it is to find this thing. Try to spot where it is. So this is actually the data that we were taking. We had so our pan-stars team, we've worked with collaborators around the world, and we got this beautiful thing. This is actually done with an instrument that Gunther was partly responsible for having been constructed. So this is a fabulous instrument. We're very lucky to use it. Boom, blue, hot, bright, and blue, and then it starts to fade and turns redder and redder and redder, just in a matter of days. So this is unlike anything we've ever seen before. So here's again, this is not a true simulation. This is an artist representation of what's going on. And it's quite complicated. You have these neutron stars spinning in. They merge, they throw out a little bit of material. You get the gamma ray burst, then you get this blue kilonova. It slowly turns red, and the jet turns into a radio remnant that we are still tracking today. So it's a complicated object. So on the left is the same thing we just saw. It's on the other side it's flipped now, okay? And what you'll see is as it fades from blue to red over here, here's the spectrum. Okay, this is the light broken up into the colors of the rainbow from blue to red. Actually, the visible range is right about here. This is down in the infrared. And this is the result of all the telescope. We took all the data taken by all the folks, put it all together to make this assembly. And it starts off very blue, and it fades very quickly. And it pretty much has that characteristic shape of something that's just hot. Okay, there's a little bit of structure in here, but this overall shape is something that's just getting cold. It was very hot and just getting cold. Remember those spectrum of hot things? That's just something cooling down. And the time scale for that, why is it cooling down? Well, it's initially heated by this beta decay, and as the beta decay slows down, it cools off. Okay, here's the light curve. Here's how we classify things that explode. Here's the time in days, and here's supernova. And typically supernova take, 2 weeks or so to get bright and then peak and then start to fade. So they last a few weeks. Here's this kilonova. It's fallen like a rock, wham. A few days and it's dropped incredibly. Okay, so it's we've never seen anything like this. So we knew very quickly that this thing was fading very quickly. And the physics that's going on is something very, very different than a supernova. So we knew immediately, yep, something different is going on. And then these are these spectra again, where you have the color and the brightness going here. And the black ones are the kilonova, and these other colored ones are typical supernova. And you can just look at this and say, yeah, that's not the same. The black is not the same as the colored ones. Here's the black here. The black is not the same. They look radically different. This is something we've never seen before. These supernova, we see these all the time. Never seen anything like this. Okay, well, this is one of those spectrums. This is a spectrum obtained by our team and our collaborators. And we were fortunate in that we had a young group of theoreticians who were very young and very smart and very hungry and very good, and all those things help. And to try to model this thing. And they took some computer code and they went and they dug up some more atomic data and they added to it. They took modified a supernova code to try to fit all of this. So the black data is what they observed. So again, here's wavelength going from blue to red, and here's how bright it is. And the blue is if you just fit one of these thermal sources, this thermal curve. So it's pretty darn close to that, but it falls below down here. And the red is what happens when what they produced with their model. And in their model, they put the absorption of two elements. Remember how if you've got this material in front of a thermal source, it absorbs the light and removes it, and you have this fingerprint of light removed, the dark absorption lines? Well, these sound pretty random. The cesium and beryllium, there's two elements here. And here's their narrow lines. But this thing is coming out at 20% of the speed of light. And so those lines, because there's all this thermal motion in the material, those lines get broader and broader and broader. In fact, that tells you how fast it's going and what the variation in the speed is. So we were able, you can look by your eye and see how well the red line fits the black line, to fit what we observed by saying, oh, there's an awful lot of cesium and tellurium. Well, that sounds pretty weird, but it fits the model quite well. I would say that's a pretty good fit. All right, well, here's a computer simulation of building up all the elements by the R process. So we're adding neutrons faster. This is happening in seconds, going really, really quickly. Adding tons of neutrons. These nuclei are very unstable. They're beta decaying like nuts, so they're working their way up and up and up. Here's the stable elements, and pretty soon they get there, and this thing is still, it's heating up, but now it's starting to cool down, not quite so much radiation, getting cooler, 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 fading, fading, fading. And here's the abundance. This is how many. Here's the atomic number. So, the atomic number, which is the mass. And this blue light is what's, the red has been what's produced. The blue light is what we observe in the world. This is how much of each element. Here's each element working your way up the periodic table. And the blue is what we've measured, basically by digging stuff up with a spoon, but lots of other more complicated techniques. And the red's what comes out of this model. And it fits this stuff pretty well. And the two elements right up here at the peak are right there, and actually that one right there, that are the most abundant of this light R process peak are tellurium and cesium. Spot on. Okay, well over here is gold and platinum. That's what the two at the peak over here. We didn't see any gold or platinum. So what we can say, we found cesium and tellurium. That's that blue region, the light R element processes. So we can say that there's other R processes, everything up to 82 neutrons. That includes silver, that includes iodine, but it doesn't include gold. But we can say all of that stuff is there for sure. We see it, we see the cesium and tellurium, that means all that other stuff is there. And we show that the kilonova is powered by beta decay, so the whole picture hangs together. But what about gold? If you were reading the newspapers when this happened, everybody said, gold! Well, I'm certain gold was made, but we didn't see it. Here's the infrared, so we didn't get, again, everybody's fighting for telescope time, and so trying to get infrared, you see this stuff best in the infrared, and you're only expecting to see it later on in time as it gets redder and redder and redder. So here's the black data, is data that other people got, is the data, and then to try to match that data, they didn't have the same group of bright young theorists, so they had to take models out of the literature, and they started combining models. Well, here's a blue model and a red model, and you add together and you get the purple model. And it doesn't fit the data. And in each case, as time went on, so there's 1.5 days, 2.5 days, 4.5 days, 7.5 days as it's fading, fading, fading. Oh boy, here by 7.5 days, can't fit it at all. Now, it might not be that the model is wrong. There's a sad infrastructure story here. I showed you that picture of having all the spectra of all the elements in the periodic table. But that data is very, very, very incomplete. We rely on the national laboratories doing their work to make those measurements, to build up the libraries, to build up the database of elements. And it's sadly incomplete. And so this could be that we just don't have the right data. We really, really need to go out and take more of that laboratory data, but it's not supported and it's not being done. So what we think happened was, whoops, is that we actually saw it off from the side here. So we didn't see the gold because if we'd been looking from the side, we would have been looking through all this high capacity stuff and we would have seen gold. But we think our orientation with this particular one was off at the side, and so we just saw the silver and the iodine up here. And of course, if we'd seen it along the jet, we would have seen the gamma ray burst. Well, if you go back to the gravity wave data, that data actually, because it's sort of this funny three-dimensional data, says that the viewing angle was about 31 degrees from the pole. So the gravity wave data actually agrees that we were probably looking in at some angle from above, and it's not surprising that we didn't see the gold. So, at the beginning I started off, what's the key question for the evening? What's the history of every atom on Earth? Well, the hydrogen and helium were created in the Big Bang. Most of the elements up to iron are built up by fusion in the center of intermediate to high mass stars as they burn up their nuclear fuel, and it's then dispersed into space. But most of the elements heavier than iron were formed in this collision of two neutron stars. It's a phenomenal thing. That is where all the stuff heavier than iron came from. not all of it, because you have some of these S-process isotopes. That stuff got filled in later on in stars. So early on in the history of the galaxy, we just had the R process. Now we've added the S process, so we've got more and more complicated isotopes today than we had then. But originally, it was done that way, and the S process just fills in the cracks a little bit. So we are all stardust. We've known that for a long time, but there's this new strange part of the stardust. Some of the stardust, some of the material in your body came from the merger of two neutron stars. In particular, iodine did. The iodine was one of those elements that's in that group that we saw. Without iodine, you would die as surely as you would die without oxygen. Take a little bit longer, but iodine is absolutely critical to our survival. In fact, it regulates how we feel, right? Our emotions through the thyroid gland. So part of the way you feel comes from the properties of iodine, and that iodine in your body was once created in the merger of two neutron stars. It's an amazing thing. Thank you.
Thank you very much, Ken Chambers. This was really a wonderful story, bringing us throughout the whole history of the universe and the elements, and finally up to life. And I think this is really the wonderful part of astronomy. And now we have some time, as usual, for questions. So if people are willing to take questions, we will take a few questions down here in the audience. And then later, we have the opportunity for our friends to, we have some new element now. Because the elements have been created, we also have to destroy them. We drink and eat some of them outside for our friends. So please, questions. Yeah, we have two mics actually. Go ahead.
So please, happy to answer all kinds of questions. In this business, it's so crazy, there's no stupid question.
Ken, that was an amazing story, masterfully presented. Thank you for that. Clear as could be. My question is, I know that it was a big mystery for a very long time in astrophysics about where the R process happened, and you outlined that very nicely. You needed an enormous flux of neutrons over a very short period of time. Had it been, in fact, hypothesized that it might be, in fact, the collision of two neutron stars that would produce that neutron flux?
It was. It was not the most popular theory, but as early as the 1970s, Dave Schramm and Kip Thorne talked about, the same Kip Thorne that got the Nobel Prize in the end for this, right? Talked about neutron stars doing the R process. At the time, we knew less about stellar populations, and they thought the numbers didn't work out, that this just wouldn't be common enough to produce all of that. And that's still a bit of an issue, but the fact that we found this one so quickly after we were able to find it, I think suggests in the end that it will work out. And it you know, it's one of those things where it's so beautiful it almost has to be right. But the reason that wasn't taken seriously was they just thought that the numbers you wouldn't be able to produce enough stuff, that there wouldn't be enough neutron stars. Now it looks like there probably are. And at the same time, the attempt to try to model it in supernova was just getting harder and harder, and it just didn't look right. So it all came together, but people did think of it.
Jim?
Yes, the end zone of what we saw transpire, which is the periodic table, which we find in the universe now, depends, I think, pretty much on these two neutron stars evolving with the same mass between the two and pretty much the same evolution, so they can combine within a few minutes to produce this. Now, what are the chances of binary star systems forming in this way?
It's a really good question, and it's related to the previous one, right? Can you get enough of these things that are in just the right circumstances? They don't. I mean, the ones we've showed have all been about the same mass. They don't have to be the same mass. They could be different by the one that we observed happened to be quite close, which is why all the simulations look that way. But they could be different by a factor of 3 or a factor of 4 in mass, and that would be fine. What is interesting, and now I'm going to get into a little bit of speculation here, okay, is when we look at lower and lower metallicity, things that have not been as enriched as the highest metallicity things, as we look at the farther and farther systems and younger systems that haven't been enriched as much, we actually see higher and higher abundance of the R process. That's kind of a surprise. It says the R process really did happen early on. Now, one of the puzzles in astronomy is, where's the first generation of stars? We don't see any stars that are truly primordial, that are only hydrogen and helium. So we think that there was a population of stars, and they had to be high-mass stars with a short life, that happened first, the first generation of stars. So it may be that first generation of stars, which were all very massive because they had to be short-lived, or there would still be some around today, overproduced neutron stars. You had very massive stars, there were lots of neutron stars, so that this process happened more frequently early in the universe than it's happening right now. Now, that's a hypothesis. The beautiful thing about LIGO is they improve their sensitivity. We'll be able to see this happening all over the universe as the sensitivity grows and as we add more and more antennas. So it's a fascinating question to be able to map out this whole process early in the age of the universe.
Okay, we have another question.
About the spectroscopy, how hard? You said that the laboratories, they just didn't have enough data.
That's right. And
how hard is it to?
Go ahead.
How hard is it to make a spectroscope of an element?
Well, building the spectroscope is not the hard part. I mean, it's a really good question. We should do this. I mean, I think we should have this data available. It's a shame that we don't. But it's not quite as easy as you might think, because some of these chemicals, particularly these high mass ones, are actually chemically quite poisonous, right? They're toxic. They're difficult to handle. Some of them are radioactive. So you don't want to be doing this in your high school chemistry lab. It does take a national lab to do it, and you want to do it through this whole range of pressure and temperature. So it's not easy to get all that data. On the other hand, in the year 2017, my gosh, why don't we have all this atomic data for all of them? It's just a shame that we don't. But it's a really good question. And the reason we don't is because it's difficult to handle some of this stuff.
Layman's question. It seemed like a neutron star is similar to a nucleus. So is that true? And if so, why are there no protons in a neutron star?
It is very much like one giant atomic nucleus. The gravitational force is so strong that the way it works out is if you had free electrons and free protons, they get crushed into that neutron. Right? It's the opposite of the beta decay. So you started off with something that came from a star that had lots of protons and lots of electrons, but the most compact state is to push all the electrons into a proton, make a neutron, and have nothing left but neutrons.
Okay, we maybe one or two more questions, and then we go and destroy elements.
So does this mean that during the hypernova phases or during the actual collapse of the star, that elements aren't being formed during the collapse?
In a massive star, the sort of onion layer stuff?
Yes.
Yeah, that is where everything up to iron is made. But you hit this problem that iron is the ultimate ash. You can't go beyond iron. The only way to get beyond iron is to do this thing of adding more and more neutrons. So up to iron, yeah, we can do that in stars, and that's pretty well understood. It's how to get the ones that are heavier than iron. That's the hard part, and that's where you need to just slam these nuclei with lots and lots and lots of neutrons. Did I get the question right? Okay.
Is there a last question? No. Oh, yes.
Do you astronomers know how many supernovas neutron collisions, type 1A supernovas have had to have transpired to produce the number of elements that we find on planet Earth?
Yeah, the way people have addressed this is to go the opposite of what I said, and that is to take, so the shorter answer is right now we don't, right? But you can work the problem backwards. We do know how much of this stuff there is. We have a pretty good idea of what's the natural abundance of all of these elements, and that's actually really, really hard work. You know, I joked about you going out, you dig it up with a shovel, and you see how much stuff there is. It's not that easy. It's really hard work, and some stuff you can do by direct measurement, and some stuff you have to infer. But we have what we think is a pretty good understanding of what's the abundance of each of the different kinds of elements. So you can work the problem backwards. You can go from that and say, well, how many binary neutron stars does there have to be to have produced this? And the answer is we ought to be able to see, you know, something like 1 a year of these. So right now LIGO is shut down. LIGO, they're upgrading to higher and higher sensitivity. But as time goes on, if we're not finding and you can't hide them, you can't hide the gravity waves. You might be able to hide the optical source from us by being behind dust or being in the daytime or whatever, but you can't hide it from the gravity waves. So if we don't start seeing these at a rate of something like 1 every year or every 2 years, then there's a problem. But we saw this one, 3 weeks after they turned on the third antenna. So, stay tuned, but it seems to work out okay.
Okay, let's give a big round of applause for Ken. And then thank you very much, Ken. And then those of you who are interested in a little bit more elements, let's meet outside.